Good afternoon. I am representing ABB Marine and Ports Division, and my presentation today will therefore be what we are doing in the marine business with relation to hydrogen, what we are doing today, and also share some thoughts about how we see the future for hydrogen in shipping. And the shipping industry today is entering into a transition or a transformation, which is, in my view, the biggest transformation since the introduction of or invention of diesel engines back in the 1800 something. And that is due to the environmental requirements and the IMO's targets, International Maritime Organization targets, to reduce carbon emission by 40% in 2030 and in 2050 by 70%, using 2008 as the reference level. And considering that ships that are being designed and built today will be in operations for many years to come, maybe 20 years or maybe more, it is an urgency to start to do this transition already now. And we believe that hydrogen and other fuels which are derived by hydrogen will be an important part of this transformation. A few words about ABB. I will not say too much, but for those of you who do not know the company, we are a technology company. We are focusing our business in electrification, in motion, process automation, and robotics. We are a multinational or a global company operating in all three regions as we define them by Europe and Americas and AMEA, Africa, Middle East, and Asia. And we are about equal size in all these three regions. As a company, we have also set our targets for our own sustainability, and we have declared that we shall be carbon neutral in our own operations by 2030. And since we are very much into this power transmission and power transformation in the industry, there's a lot of electrical energy which is going through our systems. So our impact on the greenhouse gas emission reduction will be even bigger when we're considering what we can do for our customers. So we have also set a target for 100 million ton reduction annually for our customers by 2030 for the systems that we are delivering from 2021 until 2030. As a company, we have this vision and philosophy that we should be a global company, but also act locally. And ABB has been in Korea for more than 50 years. We have several locations and factories. We have a full value chain from sales to production to service in our sister company in Korea. We have more than 500 employees in our operations in Korea. I will also show this reference project that we have now. This is the first domestic zero emission ferry, and we were honored to be awarded a contract for delivery of the electrical power and propulsion solution for this vessel. It is not fueled by hydrogen. This is a fully electrical vessel with battery electric propulsion and shore charging for doing the transportation of people outside of Ulsan port. It is now under construction at Haemin shipyard in Korea. So what we are doing in this business, marine business, the core of what we are doing is electric propulsion. So using electricity generated by a prime mover or an energy source to make the propulsion of the system by using electrical motors and to drive the propellers. So that is the core of what we are doing. Diesel electric propulsion was already pioneered more than 100 years ago, so it is not a new technology by itself, but it has gone through quite rapid and substantial technology development since the start, of course. We have also made a transition from diesel electric systems, which became very popular during the 80s and 90s due to the higher efficiency and lower fuel consumption, but also the operational performance and the comfort of electric propulsion compared to mechanical propulsion. So we have gone through diesel electric, we have gone through gas electric using LNG as fuel. We see fully electric propulsion vessels now with batteries and short charging. And now it is the time for us to enter into a new area where we are using carbon neutral fuel as a new energy source for these kind of systems. And in electric propulsion system, we have an electrical backbone or infrastructure in the vessel where we are connecting the energy sources to the electrical power grid, and then connecting the ship loads and the propulsion loads to the same grid and managing to optimize the power generation as much as possible in the system. And with this electrical infrastructure, it is much easier to plug in new and different energy sources as long as they can produce electricity. It is more or less to plug them into the electrical grid, and then you can start operating with the same installation as was there from the original. So what we say is that if you want to make a future-proof concept where new technologies and new energy sources are being developed as we go along, and utilize those for the future operations, then an electric infrastructure is a future-proof concept. There are two types of such electrical system. The conventional system is this, what we see on top there, that is the alternating current solution. But we also have introduced a DC grid solution where we are distributing the electrical power by using direct current instead of alternating current. And that has certain advantages. So first of all, it is more easy to connect to the different energy sources, and each energy source can be optimized by itself and not as a complete system, which gives better performance and better efficiency of each of the source and also for the consumers. There are less steps in the power conversion, so there are less losses and better efficiency. And with the DC grid, it is much faster time to recover from a faulty situation, and much more opportunities also to make robust, reliable system by using reconfiguration of the system, which is one of those, I would say, pillars and platforms that can enable also autonomous vessels in the future. So features, if we are using combustion engines, we can optimize each combustion engine by using variable speed in a DC grid. The power is distributed on DC, as I said, and it is easy to integrate alternative and different power sources. This is the rules and the roadmaps and regulations towards these targets for IMO 2050. I will not go too much in detail to this one. I will only highlight these two milestones here now. 2030, 40% CO2 reduction, intensity reduction, and in 2050, 70% carbon intensity reduction compared to 2008. And we see already that IMO has, and countries and regions, they have also already started to implement stepwise rules on this path. Okay, coming to hydrogen. So hydrogen, as we see it, will be one of the fuels that will enable this carbon reduction. And also out from hydrogen, there are different ways to use it. We can use it directly in the fuel cell, for example, or we can use fuels which are derived by hydrogen. That could be ammonia, it could be synthetic diesel, synthetic methanol, or synthetic methane. That could be energy carriers for the future ship systems. If we look at the use of the different fuels, this is a conclusion or a view from a large industrial study that was made in Europe, Hydrogen Europe, with several participants. It is a little bit smaller, so you can't probably see the text there, but I can explain. The blue here on the left side, that represents the market as is being seen for compressed hydrogen. The middle sector here, the white with the green dots here, those represents liquid hydrogen market. And when you come to the larger vessels and the longer distances of traveling, then neither hydrogen or liquid hydrogen was found kind of feasible to cover the needs for those. So there this group concluded that a liquid fuel and green ammonia would be the major energy carrier in that area. So we can see on the left side that is very much related to coastal vessels, short distance shipping, inland waterways. The middle sector, that is more regional type of vessels operating between shorter distances and shorter port-to-port voyages, while the deep sea shipping with the tankers and bulkers and LNG tankers and so on are on the right side, that probably will need liquid fuel in the future unless something revolutionary happens during the next coming years. So we see different usages and different technologies for the different vessel types, and that is also one message, that we don't see one solution that fits all. There will be a variety of solutions to be deployed into this industry. For electric propulsion and energy storage, we have seen a development where the first movers are the small coastal vessels, short distance shipping and inland waterways. They have been the fastest movers and coming first to the market to use energy storage systems, batteries and so on. While we then see a gradual adaptation to other segments like the more coastal vessels and these deep sea vessels coming also into the play. So for energy storage, we see that now all over the spectrum of vessel types. And we believe that similar development we will also see on use of fuel cells, that we will first see it on a very local trade and local routes, while it become into other sectors as we go along. So coming into what we are doing now and what we have been involved in fuel cells in the marine. So these are the projects that we have been running and we are running today. The two first on the left side, those are demonstrator units. So that was more to demonstrate that the technology using hydrogen and fuel cells are feasible for marine applications. They are not a central part of the electric propulsion system, it's just demonstrating the technology. Then we have two European Union supported projects, Miranda and Flagships. They are ongoing, where also it is a demonstration and prototyping installation on the vessel for one research vessel, Aranda, and for one river transportation vessel in France. The most recent project, that is a commercial project. It is not funded by European Union or other research fundings. It is a pure commercial project. The vessel type and the owner cannot be disclosed. That is confidential. It is an ongoing project, and there we are integrating a 3 megawatt fuel cell package consisting of several smaller fuel cells into the DC grid and electric propulsion for this vessel. So what we are doing in terms of the fuel cell itself, ABB, we are not producing the fuel cells. We are working together with other suppliers of fuel cells. So we have been working with several suppliers in Europe and in North America. So these are typically smaller fuel cells up to 100, 300 kilowatt. So we call them low power generation units. And those are the units that we have been working with in the pilot projects that I showed in the last slide. We have also started a joint development between ABB and Ballard in the US, where the target is to develop a high power unit from 1 megawatt to 3 megawatt in one unit consisting of fuel cell modules and a modular construction, so that we can standardize the design 1, 2, or 3 megawatt unit for the higher power vessels that we foresee will come in the years to come. And this shows the integration of fuel cells and batteries into the system. So here are the fuel cells, the low power generation unit fuel cells, as many as needed to provide the power for the propulsion. Fuel cells and batteries, they are two sides of the same coin. If you have fuel cells, you should also have batteries also to stabilize the load and give the dynamic performance that the vessel needs. We have the DC distribution system here, and then the electrical package here, which is driving the motors for the propulsion. And this it has also been equipped with shore charging system. So this is the concept that we have developed for a coastal bulk carrier in a concept study that has been carried out in Norway, but can easily be adapted to any other region as well. So that was actually my last slide in this one. So I just have to end by saying kamsahamnida and thank you very much.